Fabio Pasquali, who's going to talk to us about relational doctrines and quotient completions. Take it away.
Thank you. So, good afternoon, everybody, and thank you to the organizers for this standing meeting and for inviting me to speak and to present this summary of this joint work with Francesco Danilo of the University of Genova, which is about quotients, somewhat again. We spoke about quotients in this meeting sometimes in the past talk. And I want to present a construction that completes doctrines with quotients, but not all doctrines. We focus on a particular class of doctrines that we call relational doctrines, because they somewhat encode the calculus of relations. And we did that, we introduced that class to address the problem, and I want to spend some minutes to introduce this problem, this situation, let's say. So we are speaking about doctrines. We saw them many times. We have the tutorial by Pino Rosolini that gave precise definitions and examples, many examples. Among the examples, there's one that I like the most for presenting doctrines and to give an idea, a leading idea or intuition of what they can be seen. And it is the contravariant power set factor. So I keep this intuition for all the presentations. So doctrines can be seen as a function from a category C that we can understand as a category of sets. And P maps sets to subsets. So it determines the algebra of the subset of my category. And if this algebra is rich enough to write down what the equivalence relation is, I can ask if the doctrine has quotient or not. In general, the answer is negative. And in 2013, Maniche Rosolini presents a construction that fits the problem. The construction is presented in these two papers, written in blue at the bottom, and it has been developed in several papers that follows. And the idea is to take a doctrine, take the universe of sets, and producing setoids over it. So they produce a new doctrine with quotients for all equivalence relations that you can write in the language of the new doctrine. And the new doctrine has base objects, so the new sets are the node set together with an equivalence relation, so a setoid. And the new subset are those that satisfy this property that sometimes in the last talk we call it the descent condition or substitutivity property. Basically it says that we are taking those subset that sees, that believes that the equivalence relation is inequality. And indeed the diagonal predicate over the setoid x rho is right. So we are determining the new equality, the equality predicate over the new set. And so the purpose of this talk is to generalize these constructions in order to have among new examples metric spaces. So a set together with a distance rather than an equivalence relation. And what I mean for this, so the differences between the distance and equivalence relation is only in the way you write the transitivity condition, because both are reflexive, both are symmetric. Distances are written using a monoidal operation that need not mean a mean operation. So they are a linear version of equivalence relation, if you want. And the interest in taking distances as equality comes from, I don't know how to say that, so let's say approaches or methods that are used in computer science that are called quantitative. So when you say quantitative method, quantitative reason, quantitative something, is that is a sort of, let's say, philosophy that says, so you have your object of interest, let's say programs, you want to compare them, and instead of saying that they are equivalent with respect to the equivalence relation that you have, you say that they are close with respect to the distance that you have. And this is useful when you study those software systems where errors come into play, because, so this is a naive picture, but distances take care of propagation of errors. So you have your object X, you manipulate it, your program, you manipulate it, you have a new program Y, and you say that they are more or less the same, there's a difference epsilon. You do a second manipulation, there's a different epsilon, but if you compare your final problem with the original one, the difference is increased. And this is not captured if you use an inf operation, because epsilon in epsilon is still epsilon. So this is a sort of underlying philosophy of these studies that says equality should be a distance of metric spaces. So we want to rephrase the construction of setoids linearly, and an attempt might be to take those doctrines where each px, each fiber, each collection of subsets, if you want, is equipped with the monoidal operation. So not finite intersection, but some monoidal, some monoidal operation on the fiber. But this, if we repeat step by step the construction of Magetti's coefficient, this doesn't work because there's no proposition of linear logic that can be rephrased in this with the machinery of doctrine that says whenever you have a binary predicate that is reflexive and substitutive or satisfying the descent condition for all predicates, this binary predicate satisfies this entailment. It is idempotent in the sense. And if you think of D as a distance, if you pretend that D is a distance, the only distances that satisfy this equality are the trivial ones. So it says that D is 2 times D. And this holds for 0 and infinity if you take distances valid in the logical. And a problem is, well, a way to see a problem is in the substitution rule because, well, if you think of linear logic that says that formulas are resources to do something, you can see equality as an amount of resources to substitute a y in place of x. But this has to work for all formulas. So if you take phi tensor phi, the number of substitutions that you have to employ is the double. So this rule is not resource sensitive. There are some solutions, some results that go around this obstacle. So the most famous one was proposed by Mardak and Plotkin in a paper that appeared this 16, and basically every year after the 16th they present a paper that refine this very results, and they propose this quantitative equational theories where they don't work in linear logic, so they work in infinitary, first order predicate logic. So they don't have a binary predicate that can be interpreted as a distance because they don't have a monoidal operation, but they have in their calculus infinitely many binary predicates that they see as an approximation of the distance. And using the infinitary nature of the calculus, they can, once you have an interpretation of that calculus, you can build a distance out of the interpretation. So this is one of the solutions. Since this workshop is about doctrine, I mentioned also another solution that I have with Francesco Danilo, and that we present a calculus, using doctrine that we give this fancy name, but the solution is using linear logic with modalities indexed by a natural number, or more general, by an element of the same ring. And with this modality, with an index, you can reformulate substitution, putting a modality in front of the quality predicate, and the index, the number that index the modality, counts, in a sense, the number of occurrences of x, or the number of occurrences of the values that has to be substituted. So you take care of how many substitutions the calculus has to do. And if we employ the quotient completion out of this doctrine, what you have is the metric space in Lipschitz function. So that's what we do. And there are also many other solutions in specific problems, and that instead of using linear logic, instead of using first order logic, they use the calculus of relation in some categorical shape, so a mechanism, b category or something. Because the calculus of relation is variable free, it's propositional. So it doesn't have to take into account how many substitutions you have, because they are almost zero. There are no variables around. And this is what we do today, is this is part what we are going to do. So we, first of all, bring the causal relation into the machinery of doctrines. So the first thing that we introduce is the class of doctrine that we call relational doctrine, that are doctrine that takes a doctrine that speaks about binary relations. So that it takes only two sets of the same category, so always two objects of the same category, and they map to object to a poset that collects the relation from the first set of the object. And this have to be equipped with the operation of the basic calculus operations, so composition, the identity of the composition, and the converse. So we need three families of one-term functions. The first that encodes the composition of two relations. So we have two relations. The codomain of the first is the domain of the second, so they are composable. And the maps give the composition. The other picks their identity element. The other one takes the converse of the relation, so it changes. It goes from x to y to y to x. And these are the standard axioms of the causal relation. So the composition is associative. The identity is the natural element of the composition. The converse switches the order. The converse of the identity is still the identity. And if you take the converse y, you go back to the original relations. And we have also to write what happened to arrows, because R has an action also on arrows. And the requirement is that they latch preserves the relation. So they have these three inequality that are taken by what we observe when the category C is a set and R is the part of the product of the two sets. So if we take set theoretical relations, these are precisely the inclusion that we observe. So they
is this some kind of monoid object or monoidal object? So it's, because this, you can perform R with itself as a profile flow, and then it's a mapping from R plus R to R. That's the composition. Does it make sense? Or?
Maybe. You say it is a monoidal object. So you say that a relational doctrine is a monoidal object inside a category of
It's a category.
doctrines, or in a large sense. So yes, well, what we can prove if we take the category of functors from an arbitrary category to poset. So if you want the category of doctrines where we drop the condition that the base has finite properties. So an object that is a functor from a category C to poset. So this action leaves an internal category in that category. So maybe this is close to what you are saying, if I understood the... I don't know if this answers the question.
No, so what I was saying is that it looks like probably it's a monad in the two categories, post-pro functors.
Okay.
But what you are saying is it...
It's a category, it's the same thing.
Yes.
So,
I mean, in a two category, there's a notion of monad.
Okay, but maybe, I don't know.
So, but you're saying that, because I don't have products, I explicitly introduce binary predicates. Is that, so
I don't know if
you don't have products in your category C, and therefore you explicitly talk about binary predicates. Is that the intuition?
Is that the intuition? So
Okay.
to speak about binary predicate, instead of taking product, we take 2 times the category C.
Okay. But you only have binary predicates, or can you talk about unary predicates using the D?
No, if you're, so there are no assumptions on the category C. So the category C need not have products. So
Yes,
if
but what if I want to try to talk about a predicate on X?
Jonas, I
So,
think you should let him go because it's a very short talk.
Sorry.
At the end, I have a slide on this, maybe we can talk it, but if you don't have a terminal object or something in principle.
Okay, sorry.
Or there's there's another way to do this, maybe we can discuss if I have time at the end. So these are relational doctrines. Some examples. So if you have an elementary instantial doctrine, so the claim you see as binary product and subsets of the fibers are closed under this operation, you can build a relational dot in the way, the standard way, so the identity is the equality is the identity, the composition is given by existential identifier over the common variable, and the converse is simply the same relation. If you took any quantile in this presentation, we fixed the Lobelian quantile, and you can consider metric relation that are nothing but function from the product of two sets to the quantile. The identity element is this delta. The composition is given by this rule, and the operation between the two relations is the addition, so the monoidal operation. And the last examples, but it belongs to the class of example that I want to discuss, is the relational adaptive expansion. So imagine you have a category with finite limits, and a relation from a set X to a set Y is simply a pair of arrows with a common codomain. You can order span by factorization. You take the poset reflection, you have a poset, and you can build the relational adaptive spans. So the entity is the trigger span. This is the composition of the two relations, and this is the converse. You simply switch the two legs of the span. And this one belongs to a larger class of example that we want to discuss quickly, that of order categories with evolution. They are categories enriched in the category poset with an involution factor. And whenever you have such a structure, you can build a relational dot in R by extending this assignment. And all the categories with involution and relational dot may appear close. And indeed they are, and to compare them, we take a look at the category of this. So all the categories with involution are the object of this category, or CI, whose arrows are order factors that preserve the evolution. Relational doctrines can be the object of the category are the object of the category D, whose arrows are a factor from the two bases, together with another transformation that is a generalization of the relational lifting of F, so in the sensitive percent operation.
Okay. Good question. On the right-hand side of the definition, where you're using home, should the involution be applied there somewhere?
So the involution gives the converse.
Yeah, that's why I'm asking, because it should be contravariant in both arguments, but now it seems to be co-contravariant. So I'm asking whether the involution should be applied there somewhere. Or is it like a... Right, the onset functor is covariant in the second argument,
Yeah.
but it should be contravariant in both. Or am I missing something?
No, well, so the relational composition is simply the composition of two arrows.
Yeah,
And when you have, let's say, GF, so you have F in this way, so let's say this.
yeah.
So the involution is an arrow like this. And if you take the involution of the both, what happens is that the involution of F, composition is the involution of G, simply because the involution is...
Oh, I see. So you're not taking the normal composition.
Right.
You're redefining it. So, okay, thank you.
And with this definition, what we have is that the category of all the categories with involution is fully infinitely and reflexive mapped into the category of relational doctrine. And we can characterize those relational doctrines that are in the essential limits of this inclusion that are all the categories with involution. And so this, I have to open a parenthesis that is not involving the rest of the paper, but just to complete the characterization, I introduced two logical principles. So we say that a relational doctrine satisfies the rule of unique choice if whenever a relation is single valued in total, so it satisfies this two condition, it is the graph of an arrow in the base. So there exists an arrow from the domain X to the domain Y such that the relation is the graph of it, where the graph is written in this way. This is what I think is close to what Jonas in his talk called a tracking arrow. So if I'm right, the relational doctrine satisfies the rule of unique choice if every total and single value relation has a tracking arrow. if I give it time for it. The second logical principle is extensionality. That says that whenever you have two parallel arrows, if this inequality is satisfied, that says that the relational doctrine, that the two arrows are equal for the relational doctrine, they are equal in the logic of the relational doctrine, then they are the same arrow in the base. And a relational doctrine is an ordered negative evolution if and only if it satisfies these two principles. And what we can see is that the relational doctrine of spans it satisfies these two principles, so it is an ordered negative evolution. It's a way to see it. It's already known that it's a way to see it. So we are done with examples, we can fix our quotient. So in every relational doctrine we can write what the equivalence relation is in this way. So it's symmetry and transitivity. Just a side remark, so I said the character of relation is propositional, and if you remember the tutorial by Pino, it says that variables are projections, and here you see, but also before, but here I think it's clear that there are no projections around, also because C can be without products, so there are no assumptions. This is a way to see the variables free net of the calculus inside the doctrine, the absence of product in the base. So this is the definition of equivalence relations. If an equivalence relation in the metric examples and in the relational doctrine of metric relation are precisely distances. In the relational doctrine of spans, the equivalence relation of the pseudo-equivalence relation of the base category. And if I take a doctrine that derives from an elementary existential doctrine, the equivalence relation are the same equivalence relation that I could have written in the original doctrine, so we are not losing anything. Quotients, well, this is a sort of standard rephrasing of many definitions of quotients, and we say that an equivalent, a doctrine has quotient for the equivalence relation if it has an arrow in the base that satisfies this condition that says that the relation, the equivalence relation is the kernel of the quotient arrow. And for every other arrow satisfying this inequality, where for every other arrow such that the equivalence relation is included in the kernel, there's a unique arrow out of the quotient that made the triangles to you. So not every relational doctrine has quotient, and the construction that complete a relational doctrine with quotients is written like this, with this notation. And the new base category is still a category of setoids in the style of Maletius unique quotation, so objects are pairs, an old object with an equivalence relation. Arrows are those arrows that preserve the equivalence relation, where two arrows are equal when they are equal with respect to the names of the god. The functor takes two objects of the base and considers those relations that satisfy this condition, that is the descent condition written propositionally, written without markers. And the actual arrow is given on the represent. It doesn't depend on the choice of representing the given variables. So this factor is a relational doctrine with quotient. Quotient are given by identity, so as in the standard way. And this construction is universal. We can set up a number of categories of relational doctrine with effective quotients, and they include this construction provides the left of jump to the inclusions. And if you take a look at examples, if we apply the construction, the category of metric relation, what we have are B modus in the sense of Lovia, so metric relations that are substituted with respect to the distances, over the category of metric spaces and non-expansive maps. If we apply this construction to the relational doctrine of spans, what we have is the relational doctrine of jointly monic spans over the X with X completion of the category C. And if we take the metric extension doctrine, we build the relational doctrine, we complete with quotient, we have this strange beast. But we can do also the other way around. We complete with quotient the doctrine using Maletius construction, and we produce the relational doctrine out of it, and what happens is that the two constructions are the same. So we get the same. So this is the end of the talk. The initial purposes were recover metric spaces, and this is okay. extending Maglietta-Mussolini construction, this is more delicate. And the last slide is on the comparison with the two constructions. So we saw that if we have an elementary existential doctrine, so a category C, final product, and this algebra of operation over the fibers, we can build a relational doctrine. If we take a relational doctrine, is this relational doctrine equivalent, isomorphic to some relational doctrine that comes from an elementary existential one? But the answer, we already know that the answer is not, because we saw that from an example that there's no way to build the product in the base category. Among the equivalent relation of spans is based on the category with weak finite limits, so also weak products. So there's no way to build products, but we can refine a little bit this inclusion here and taking the subcategory of relational doctrine on those relational doctrine whose base has finite products. And in that case, so the work is in progress, but an attempt that we can do is to, so maybe this answers the question that was before. We can take a relational doctrine and fix one of the components, I choose the second, to be the terminal object. So a relational doctrine over two objects, one of which is a singleton, is a predicate, is a subset, this is the subset, not the subset of the product, but the subset of the set. So the intuition is this. Does it work? Does it give some, maybe the inverse of this inclusion, an equivalence or something? Can we recover this operation from this? Well, what we know is that if we take an arrow, the ring, and we take a subset of B, an element in the fiber over B, the indexing can be written this way. But if we take the subset of A and instead of gamma we compose with the compass of gamma, we get the left adjoint to the indexing. So relational doctrine always have left adjoints. Does this left adjoint satisfy some Bechdel Frobenius? Can we combine other operations to have the other part of the definition? That is something that we don't know. So for now, the characterization is the trivial one. So we assume everything that we can do, and we know that we have assumed product, but the other maybe there's something that we can recover, something not. But for the moment, the characterization is this. And now we finally can compare the relational quotient condition and the quotient condition given by Maglietta-Mussolini, because if we work on elementary extension doctrine, then yes, this condition is an extension of the one that they gave. But if we bring things to the minimal term, the construction given by Maglietta-Mussolini need not the existential part to be formulated. So it works on those doctrines that are only elementary and not existential. And so if we bring things to the minimal term, the two constructions, the two words are separated. So doctrines, the doctrines that they use have product in the base, in relational doctrine don't, but the relational doctrine always have left adjoining, elementary doctrine need not have. So there are different things if we stay to the minimal, to the ground. Okay, so this is it.
Do we have questions? Go ahead. Now it's your turn.
At the very beginning, you had this result saying that if something is reflexive and transitive, then it's equivalent to its conjugation or something.
The very sugar not but okay. I can write it.
Have you thought about what happens when you drop?
We can open the...
Okay. But anyway,
have you thought about what happens when you drop reflexivity? When you drop reflexivity?
No.
Because if you want to think about partial equivalence.
Yes, but okay. So this is a question that we are thinking about, because the partial equivalence relation, at least with predicates, okay. The partial equivalence relation, at least with predicates, is a composition of two constructions. So you have your doctrine P,
yeah,
and you map the doctrine with the partial equivalent relation.
Yeah.
And these construction factors to...
Yeah, in the Cartesian case it factors, okay, but maybe not in the
No,
monoid.
okay, that's the point. So what things that we are looking is a way to, because we can complete with reflexivity, without reflexivity and see what happens, and what we are looking for if there's a way to write this also in the relational case. Because this composition says that your partial relations are reflexive in some other word that lives here. So it's not true that reflexivity comes not into play in a sense. It is hidden somewhere.
Okay.
So I will not have an answer, but maybe this is a problem that appears somewhere if you try to do partial equilibration instead of equilibration.
We have maybe the motivation for doing this work was that we wanted to have more examples than with the method completion, and with for example with the Lipschitz metric space. And but could you do ad hoc quotient completion for those? Have you thought about it? About
For the Lipschitz, the one in the we did a quotient completion for those.
And does it go as an example of this? Is it an instance?
No.
And why?
So why? Because for in the Lipschitz case, the word that I mentioned, we have a modality. So we have our fiber. For every fiber, we have a modality. We take. I write natural numbers. I could have written any centering, and that works in good ways. It takes a number, it takes a formula, and gives the modality. There's nothing similar in the relational doctrine that I presented. Maybe we can find relational doctrine with modalities that, in such a way that this case is an instance of. But I don't know.
I missed. What is the killer example of the quotient completion of the relational doctrine?
So the two killer examples are the metric spaces and the X-less completion without products. Right.
Well, with the quotient completion, I mean. For the quotient completion, which are the key examples of the...
So the first two, so the metric spaces is a result of the completion. So the first is the one we're looking for. This comes somewhat for free, but it was nice to mention because it is an example where the base category need not have products. Because this has products, so...
Yeah, but these are quotient completion.
They are quotient completion. This is, on the right, there's the result of the completion applied to what is written there.
So you have captured the three properties of this...
Yeah.
Very good. Well, cool. Thank you. Thank you very much. And from what I